Okay, welcome back guys. This is going to be a video about TOC computation. And so for TOC computation, what we are looking for is we are trying to see the response of well logs to the organic matter content. This approach works for non-reservoir rocks. In reservoir rocks, we don't usually have we don't have organic matter content, right? So the limestone cases can be tricky because sometimes you have not very clean. Sometimes you have reservoirs that are clayish, or they have some percentage of clay and shale, and sometimes there's interbedding, so that can be complicated. But usually what we are looking for is in non-reservoirs how to detect, how to see the reaction of the response of the logs and correlate that to a percentage of organic matter content, or TOC, which is the total organic carbon. So what we are looking up here is two logs. We're going to be using two logs for this. Usually you use one porosity log and the other is going to be a resistivity log. The porosity log can be either a neutron porosity or a density or a sonic. So here normally what we use is the sonic one and the resistivity one. So what we are looking to do is we need to calibrate, we need to localize or find a baseline. Where is the baseline? Baseline are areas in your field or in your well that have low TOC values. That's where we calibrate. So if we already have some data from laboratory, like pyrolysis data or things like that, or core analysis, or if you already have an idea, you know your formations, you know which areas have higher organic matter content and low, you try to find the lowest, the one part with the lowest, and you calibrate your scales in that part. How do you calibrate the scales? You need to have in mind that each log cycle or each decade has to correspond with 50 units of sonic. So having that in mind, you start, like, let's say you keep your resistivity the same, and you start varying like the sonic until you get the two curves together in your baseline, in the area where you already know, or the area where you know that there's the lowest TOC values. So you start modifying. Let's say if you're going from 0 to 200, then you start varying to, let's say, 10 to 210, 20 to 20, 30 to 30, and things like that, and so on. And even you can go back, let's say, to 190, and minus 10. So we are keeping, like, in this case, we're keeping 4 cycles because we have 1, 2, 3, 4 cycles, but in order to have 4 cycles, each of 50 equal to 50 microseconds per foot, sorry, you do need to have 4 units. That means 200 units of the sonic. So you can start varying, the limits, but the total should be 200 always. Okay, if you're working with 4 cycles. If you have more, well, it's going to be 250. Yeah. So you start calibrating that until you get the two curves together in your clean zone, clean in the sense that you don't have high TOC, and then the separation between those two curves is gonna be your indicator of your organic matter content. Okay, this distance or separation is called delta log, and there is a formula to calculate TOC from your delta log and your maturity level. Okay, so this method is pretty straightforward. The only thing that you have to have in mind is that this method only works in non-reservoirs, right? To identify the rocks organic rich in the non-reservoir rocks. And you need to have in mind as well that the maturity level. Okay, that's because for example, if you have let's say that this is the area where you calibrate. I mean, you have, this is a non-reservoir high gamma ray, right? We don't have any organic matter content here. This is inorganic, so we calibrate here. We put the two curves together. And also, I forgot to mention, the scales have to be inverted. Like the resistivity can increase to the right side, but the sonic has to go the opposite direction, so that when we see an increment in both curves, we see a separation between those two curves. Okay, so here we calibrate, and obviously when you enter a reservoir, you're going to see a reaction or response to the porosity log, because there's a porous material. But you have to have in mind that, okay, here we don't have organic matter content, because this is a reservoir and we're focusing on non-reservoir, right? Higher gamma ray. But when we see a separation, let's say here or here, we know that there's a potential indicator of organic matter content. But also you have to take into consideration that if the source that has the kerogen or the organic matter content is immature, then you are going to see a deflection only of the porosity curve, not the resistivity, because the resistivity responds to the fluids, right? So if the rock is immature, is not generating hydrocarbons, the resistivity is not going to go up, but the porosity curve is going to go up, it's going to increase. Okay, so you're going to have some separation. But if the source rock, the one that has organic matter content or kerogen, is mature, it's going to start generating, and you're going to see an increment of the resistivity curve and also your sonic curve. Okay, here we have another reservoir. We see a deflection of the porosity curve, but not the resistivity curve, because it's filled with water. Okay, so if you have these considerations in mind, then you can go ahead and continue like with the method. Okay, so basically in petrophysical software, you upload the two curves, you adjust the scales, and then you calibrate the thing, and you apply the formula. The formula that we use for calculating TOC according to the delta log distance is this one. So TOC is equal to delta log, which is the separation distance, and here we have LOM, which is the maturity of the rock. So for that, you need to look for theoretical data, or if you have pyrolysis or core analysis data, you can look for the vitrinite reflectance. And there is a table to convert from. You need to find a table that converts vitrinite reflectance to LOM, and then you plug in those LOM, and if you have LOM and the distance, the separation distance, then you can calculate your TOC. Usually in petrophysical software, this is already programmed, so you just have to like give the software the maturity value, and he's gonna calculate the distance himself. Basically, like obviously you have to, once you choose the baseline, the software does all the rest, you know. So the only thing you need to have into consideration to be precise choosing the baseline, and to be precise in choosing the maturity level. Okay, and also like for visual purposes, you can just, for example, for visual purposes, you can calculate. Let's say here we can see the difference between the two logs, right? This is the difference between the resistivity and the sonic. Here we have S2 values, which is the hydrocarbons generated from pyrolysis. If you have core analysis, that's great. If you don't have, that's okay, but you do need to have to know where you're going to calibrate. Okay, and here we see the TOC computation, and also you can actually compute a curve that shows you how much delta logs separation you have on each well. That way you can see the differences in different formations. How the TOC is varying across wells and across different formations. Okay, and compare them to each other. So basically that's what I wanted to say for today. This is a way of computing TOC, organic matter content, and this is very useful in unconventionals, but also is very useful in let's say not only trying to see potential source rocks, but also computing TOC for correcting the porosity curve of some semi-conventional or semi-unconventional reservoirs. Okay, so TOC is very necessary for correcting the density log, and so that you can have better accuracy in your porosity models, with the density curve. That's pretty much what I wanted to say, and I will be continue this series next time with another video on petrophysics. Thank you so much for listening. I see you guys another time.